So, in the last class we stopped at the discussion of having three mutually perpendicular two-fold axes generating the 2-2-2 combination as a possible point group. 2mm is another possible point group, and so on, and with respect to 3-fold, 4-fold, 6-fold, and then also the combination of 2-3-3 and 4-3-2 giving rise to axes in different directions. We find that there are 6 plus 6, so 12 additional point group symmetries which come up. We have to therefore consider the other combination. We see here it is the proper, improper axis. Here we have to consider an improper axis with a proper axis. Obviously, by the satisfaction of the Euler's theorem, it has to be IPI. We can also have IIP. So, these two combinations now will give rise to newer possible point groups, and those are listed here. We are not going to find out how they come up and how to derive it and so on. The best way to do that would be to take a course on group theory, and if someone is interested, there are group theory courses also available in this program. So, if they take the group theory course, there will be a possibility to understand how to get to the other. This is not in the scope of our course, but what we notice here is that this will introduce 4 new symmetries. So, this 2mm or M to M is one and the same. See, again I will repeat, 2 to 2 gives rise with PII we get 2mm. Now, that means that there is a two-fold axis along this direction, let us say, and M in these two directions. Now, if I go to IPI, that means I should have a M to M. So, the symmetry will be M to M. Because they are at 90 degrees with respect to each other, and we have a very nicely defined rectangular coordinate system in this particular case with 90-degree angles between them, whether we have a mirror here or a mirror there or a mirror there, it does not matter, and so also the presence of the two-fold axis. And therefore, M to M and here in this case MM2, they become one and the same as 2mm. So, there is no need to have additional point groups coming in this combination. On the other hand, in this combination an additional one comes because 3 bar is something different from 2 bar, because 2 bar becomes M, whereas in case of 3 bar it is different and it is a standalone symmetry, and therefore you get 3 bar 2M. Similarly, 4 bar 2M, 6 bar 2M, and you also have in this case 4 bar 3M. So, these 4 additional things will come in. On the other hand, if you have IIP combination, all these combinations PII will be repeated here, and in this case also it is repeated, and therefore we do not get any additional point group symmetries. So, we have therefore 13 plus 16, that comes to 32. So, that comes to 29, not 32. So, what is happening? What is it we are missing? Because we want 32 point groups and we are now getting 29. What happened to the other 3? The other 3 will come as a simultaneous presence of proper and improper. You see, in the previous slide we had this proper and improper axis simultaneously present. Okay. So, we have to therefore consider the combinations of proper and improper axis being simultaneously present, and if we consider that, we get these additional 3 possible point groups. For example, if you take 2 by 2, 2 by 2 bar, 2 by 2 bar, 2 by 2 bar, this is proper, improper, proper, improper, proper, improper. You get a new point group symmetry which is 2 by m, 2 by m, 2 by m, which is not present in this combination, because 2 by m, 2 by m, 2 by m is not generatable by these operations, and therefore 2 by m, 2 by 2 by m, 2 by m, 2 by m, 2 by m is a new point group. So, on the other hand, 6 by m, 2 by m, 2 by m is also a new point group with 6 to 2, and with 4 to 2 also we will get an additional point group. The rest of them do not appear, and as a consequence we have 3 more. crystallographic point groups with more than one axis, each axis being proper and improper simultaneously. That is what this table says, and this particular table therefore now concludes that we have 29 plus 3, which is now 32 point groups. So, these are the various ways in which we represent the 32 point groups. So, let me recount. We can go back here with a set of proper axes 1, 2, 3, 4 and 6. We get the combinations of 1 bar, 2 bar, 3 bar, 4 bar, 6 bar, which is now the improper axis associated with the proper axis. Okay. Whenever we associate an improper axis with proper axis, we get a new point group, and therefore, this is 5 plus 5. We can also have proper and improper axis simultaneously operating at a point, and that gives rise to 3 more, which is 13. And then we see the combinations that are possible. We consider not just the PPP, we consider the additional PII, IPI, IIP, and these combinations will give rise to another 16 of them. So, 13 plus 16 give us 29, and then the aspect that we can combine both proper and improper axis simultaneously gives us the 3 more, and therefore, we get the total 32 point groups. Now comes the beauty. Now comes something which we have not anticipated or not bothered to understand over the years. When people said that there are 7 crystal systems, we believed that there are 7 crystal systems, and that was a belief rather than actually a proof. And we also knew, of course, there are 32 point groups. Most of us in the college days, we learned the presence of 32 point groups. But now what happens is that if you now take these point groups and classify them, if you classify them into various classes where the importance of the angles between them becomes crucial, sorry, the importance of the angles between the axes becomes crucial, then you see that we can classify them into different crystal systems. So, this gives rise to these so called 7 crystal systems. The first one is the triclinic system, where we have a non-centrosymmetric possibility. That means there is no center of inversion that is present with this unit cell, but this unit cell can exist by itself. So, the symmetry that is associated with this is 1, and then when we combine this with the centrosymmetric combination, the center of inversion is put in, we get a 1 bar. We will not right now worry about this so called Laue class or the lattice point group, nor worry about the geometry of these 7 crystal systems, because the geometry of the 7 crystal systems we will automatically get as we see in the next class maybe, or even today, later in today's class. But what is important is that the 7 crystal classes have the point group identification with them associated with them is identified here. For example, if you take a monoclinic system, you can have a 2-fold symmetry or a mirror symmetry, which is 2 bar. Now, both of them do not represent a centrosymmetric system. Now, I am going to clarify this issue, because you may say that the 2 bar is a combination of 2-fold and an inversion center. So, how come it is non-centrosymmetric? It is non-centrosymmetric because you now examine your equivalent points. If you examine the equivalent points, in case of the mirror symmetry, it is x, y, z and x, y bar z. We operate x, y bar z mirror again, we go back to x, y, z. We do not see the presence of the inversion center. Even though mirror in principle is a combination of the 2-fold and the inversion center, it does not generate an inversion center. That is very important, and therefore, we see that the so called non-centrosymmetric systems, where there is no center of symmetry automatically coming in to the crystal system, this is either 2 or mirror, and in case centrosymmetry it is 2 by m. Orthorhombic symmetry, we already saw that it is 2, 2, 2, and the combination MM2 is allowed and MMM is allowed. MMM is actually 2 by m, 2 by m, 2 by m. We will prove all these issues with respect to the fact that the geometry of these crystal systems, why these geometry now defines incorporating the point group. So, the presence of the point group forces the crystal system to go into these crystal systems, forces the molecule to crystallize in these crystal systems. So, the molecule when it crystallizes, it first sees the point group, hopefully. We do not know, this is a chicken and egg problem, whether the molecule decides to do what kind of crystal it should go into, or the crystal system decides what molecule should come into its crystal system. That is an unanswered problem, even though there are indications that the way in which the molecules associate themselves will decide. That means the functional groups on molecules will decide what kind of a crystal system they go into, but that is something which is not unequivocally established. What happens when you crystallize a given material is that there is what is known as a nucleus which is formed initially, and this nucleation, how it is formed and why it is formed, at what rapidity it forms and so on, has never been understood. So, crystallization phenomena, even though you control temperature, pressure and so on and crystallize the materials, it is a kinetic way of crystallization, is governed by the kinetics of the situation. Kinetics of the way in which we grow the crystals, either from melt or from solvent evaporation or whatever techniques we use to grow crystals, it is a kinetic process. This is something which is not fully understood because we do not know what is the nucleation process that involves the crystallization protocol. Anyhow, let us go further. So, we therefore now distribute the point groups. This is a very important list, very important table in which we now classify the point groups into various crystal systems. As we saw in this diagram, the moment we have the 2 2 2, we identify orthorhombic systems. So, there is no other system which can have a point group symmetries associated with 2 2 2. Tetragonal, the trigonal systems will have 3 2 2. Tetragonal systems will have a 4-fold symmetry, and hexagonal system will have a 6-fold symmetry. So, when we actually decide how these symmetry elements distribute themselves in a 3-dimensional lattice, we will see how the nature of these orientation of the axis decides the nature of this crystal system. That means, in the case of just to give you an example, you already know this result from your earlier college days, but we have never put 2 and 2 together. For example, in the case of a triclinic system, we say A is not equal to B, not equal to C, and the interaxial angles are not equal. Now, the only symmetry element that can be present in a unit cell of that type is either 1 or 1 bar. That is because it is a point operation. The moment we bring in an axis operation, we will have to bring in additional symmetry that is associated with the lattice. So, in a triclinic system, in other words, you cannot have any axis of rotation. In a triclinic system, you cannot have a mirror plane. In a triclinic system, you cannot have three-fold rotation, 4-fold rotation and so on, because triclinic systems are restricted to either by themselves or the maximum they can have, maximum symmetry they can have is a center of symmetry, as is shown here. And in fact, that is what is referred to as the Laue class. This is the maximum symmetry to which it refers to, and this is what you will find when you do the X-ray diffraction experiment, which you will learn later on. And then what also is indicated here is the maximum symmetry that will get associated with this system, which is the so called lattice point groups. We will work out these two issues, as I mentioned, later on once we do the diffraction theory. So, at this particular stage, therefore, we have now done the following. We have found that in a periodic system, we get this periodicity only because of the fact that we restrict ourselves to 5 axes of rotation, and then we restrict ourselves to a point about which we can have a center of inversion, and we also restrict ourselves to the fact that whatever combinations of symmetries we can have is restricted to these many. And as a consequence, we found out that these many operations in crystals with or without translational symmetry, leaving out the screw operations and the glide planes, the operations will coexist, and that gives rise to the so called point groups. So, if the operations are independent like this, the proper axis, we have 5 point groups, 5 point groups coming with improper axis, proper axis and improper axis combinations will give rise to 3 of them. And then if we have more than one, they follow the Euler's symmetry. If more than one symmetry intersects at a given point O, then the third one is automatically invoked, and based on that we will get additional possible point groups, and therefore there are totally 32 point groups. You see that as the lattice nature changes, you will see more and more increasing number of point groups which can be associated with it. So, the moment you have a tetragonal system, you always have a 4-fold symmetry. You have a trigonal system, you always have a 3-fold symmetry. Hexagonal system will always be a 6-fold symmetry. Cubic system, as we saw, there is no 90-degree angle information here, so you will have a 3-fold symmetry along the diagonal. So, the presence of the 3-fold symmetry along the diagonal distinguishes a cubic system from a trigonal system, where the trigonal system has a 3-fold axis about one of the axes. So, these are some of the issues we will discuss more and more as we go into the 3-dimensional lattices, and then from this point groups how we can go to 3-dimensional space. What is that which generates combination of point groups with the crystal systems and the behavior of the translational periodicity that is associated with the crystal systems, which generates eventually what we call as the space groups. So, we will then see how the distribution of the symmetry elements goes to the symmetry to the space groups information. Keeping this part in mind, we should always be reminded, and that is why this next slide, we should always be reminded that the crystal symmetry and the molecular symmetry are different from each other. It is not necessary that a molecule with a certain symmetry should crystallize with the same symmetry in the crystal system. For example, if there is a system which is now like this has a very high symmetry, this is the point group symmetry which is indicated for each of these molecules. So, we can identify the symmetry that is associated with each one of these molecules. Take for example this case. This particular compound, which has a fluorine up there and a fluorine down here, is having a center of inversion at that point. The presence of the center of inversion at that point will make this molecule possess the center of symmetry. What crystal system it goes into is unknown. It depends upon what kind of interactions that this particular molecule, which has a center of symmetry, develops with its neighbors in the 3-dimensional lattice. So, remember that in a crystal, when you grow a crystal, it is a 3-dimensional unit. So, the basic repeat motif is this molecule. So, this molecule now let us say crystallizes in some space group. It is not necessary that it should crystallize only in a triclinic system. It can have a higher crystal system depending upon the way in which this is packed inside the unit cell. This takes you back to the Escher's diagram. You remember we talked about the Escher diagram, and in the Escher's diagram one issue we put in very strongly, that is the close packing. So, when these kind of molecules pack into the crystal lattice, they remember that they should pack closely, and the nature of the close packing is crucial, and the way in which the close packing is decided depends upon the interactions this particular molecule develops with its neighbors, and these are known as intermolecular interactions. We will be spending some time towards the end of the course on understanding these intermolecular interactions based upon the nature in which these molecules assemble themselves. At this stage, I was already referring to the work of Kitagorowski. Kitagorowski said that if the molecule has a symmetry, and this particular symmetry will be found and must be found in the crystal structure as well, invariably the molecular symmetry will find itself very comfortably settling down in a crystal system which has 1-bar symmetry. It does not mean that it should crystallize, this particular molecule should crystallize in a monoclinic system. I would suggest that you refer to literature and see this particular molecule and see what crystal system it goes into, just to keep the curiosity alive. Similarly, what happens to this planar 6/MMM, which is the symmetry that is associated with benzene? Benzene is not going to crystallize in a hexagonal space group. Find out where benzene crystallizes, under what conditions benzene crystallizes. So, this opens up the possibility of molecules crystallizing in more than one possible crystal system, and this is where the interest comes in pharmaceutical industry, because pharmaceutical industry wants molecules to crystallize in different crystal systems, because the physical properties associated with the crystal depend upon how the molecules pack inside the crystal lattice. The physical properties, by which I mean the melting point, the solubility, the so-called bioavailability, which is very crucial for pharmaceutical materials. They need to have the molecular symmetry and the crystal symmetry go hand in hand. Because of the fact that the molecules, they are very clever, they keep their symmetry. Benzene cannot be other than having a planar 6/MMM symmetry, but for example, a cyclohexane can have both it can have a sofa configuration, it can have a half chair configuration, it can have a twist chair configuration, it can also have a chair configuration. So, depending upon the type of substituents you put on this particular crystals of this molecule, it will decide which kind of a minimum energy configuration it would like to adapt. So, it has this flexibility, whereas here there is no flexibility. Now, because of the fact that there is no flexibility here, it does not mean that it should crystallize in a system which has this 6 by mm space group, 6 by m, 2 by m, 2 by m space group. So, the space group in which it crystallizes, once again I suggest you refer to the literature, find out in which crystal system benzene goes into and under what circumstances, because we all know that benzene is a liquid at room temperature. So, when you crystallize, you have to do some tricks either by reducing the temperature or by applying pressure, and then find out what happens to the crystal structure. So, this therefore gives rise to the possibility and an innumerable number of possibilities, particularly in pharma industries, to design what they call as polymorphic modifications. So, each and every molecule shown here can have different kinds of polymorphs, and the presence of polymorphism is crucial for the pharmaceutical industry. So, there is an application potential right away coming up for the industry people. This is also true with materials, because depending upon the type of molecule and the molecular property, the material property will be decided once again by the nature in which it packs itself inside the crystal lattice. So, the crystals therefore not necessarily should have the property of the molecule, but the molecular property can be tuned to the property of that could be displayed in the crystal system. So, this therefore opens up the possibility of studying more than one crystal structure of a given molecule, and so polymorphism issues both in material science and pharmaceutical industry become important. So, that is why I showed some examples of molecular symmetry here, just to tell you that, for example, the presence of MM2 symmetry in this does not mean that this molecule will crystallize only in the orthorhombic symmetry. It can crystallize in many other symmetry. So, the symmetry of the molecule is not necessarily the symmetry of the crystal structure. So, this is what I was telling, that if there is a tetrahedral carbon with AB substitution, there is a tetrahedral combination with all A kind of substitution, you see that the point group symmetries are different. The crystal symmetry may be very much different. So, this may crystallize in a tetragonal system, this may also crystallize in a tetragonal system, but the molecular symmetry is still kept intact. When the molecular symmetry is found to have a certain information which it can use in the crystal system, when the crystallization takes place, the crystallization will be in such a way that the molecular symmetry is kept intact, and therefore, it is very likely that the symmetry in the molecule is not destroyed. What is destroyed is the way in which the molecules are arranged inside the unit cell. So, the question of minimization of energy comes in. This is how prediction of crystal structures has become a very big issue, because unless you make a crystal and solve the crystal structure, it is not possible to a priori predict what crystal system this molecule can go into. And this has been an exercise which has been practiced over the years, and I must mention that at this stage that we have not achieved anything significantly appealing in order to say that, well, I can predict the crystal structure given the molecule. People have done this exercise. This area is called crystal structure prediction, and this crystal structure prediction area is now a very flourishing area, where people are taking the molecules and then predicting the possible crystal structures into which they can go based on various thermodynamic and kinetic parameters. They are trying to control both the thermodynamic and kinetic parameters, because I already mentioned that crystallization is a kinetically driven phenomena. So, based on that, energy minimization of energy is performed in a possible unit cell, which then is modified such that the minimized energy configuration eventually results for the closed packed crystal structure, where we have the molecules closely packed in the unit cell. So, the unit cells are defined and the possible structures are predicted. For example, structures of very many pharmaceutical compounds are earlier predicted, but the problem is that it either goes into one of the possible predictions or it will never go into one of the possible predictions. So, the conclusions drawn from crystal structure prediction are still to be tested. So, this approach of crystal structure prediction using molecular dynamics simulations and so on is a upcoming field, but it is not a field where we can have 100% success at this moment. So, there is a lot of improvement required, there is a lot of advances that one has to look at in terms of calculations particularly to get to the final prediction of how a molecule can go into a crystal structure. Now, we come to the operation itself, the symmetry operation itself. We are still not out of the understanding of the symmetry operations. So, the way in which this particular slide is prepared and demonstrated is to show what happens to the objects when they find themselves in a situation where they see these point groups. For example, if an object, the object is referred to by this big circle with a positive and the object is referred to a circle with a comma. Whenever this object inverts itself, we put a comma inside the object. So, whenever the object is inverted, we put a comma inside the object, and when it is coming towards you, this is shown as plus, when it is going inwards, it is shown as minus. So, in this example we have illustrated suppose we take the coordinate of this point as x, y, z, then the coordinate of this particular point is minus x minus y minus z. That means these two now are related by a center of symmetry, and the center of symmetry symbol is used here, the little circle, open circle, and the symmetry is illustrated below. So, all possible symmetries which we have discussed with respect to the 2, 3, 4 and 6 are given in this list. So, this particular list therefore has all the possible ways in which you can generate now objects in this 3-dimensional lattice. Here is one issue which I will discuss and probably stop today, that is to discuss what happens if this object is here. So, suppose the object now decides to come to the position of the center of symmetry, then what happens to this particular object? So, this then will be moved here, and then it has to generate x, y, z to x bar, y bar, z bar. Suppose this is now also the origin of the crystal system 0, 0, 0, then it will make an image of itself on 0, 0, 0. That means we will have to show this something like what is shown here. Okay, in the case of a 6 bar symmetry, you take this picture, imagine this fellow to be moved up to that particular position, and that is exactly what will happen. That means now if this is representing a molecule, the molecule now must have a center of symmetry because it has to sit on the center of symmetry, and then this particular molecule which sits on the center of symmetry is related to itself. So, the diagram now will look like taking out this fellow and pushing it to the 1 bar position. Such a situation is referred to as a special position in this condition. So, whenever there is a object which sits on the symmetry element itself, it becomes a special position in any given system. So, any point group which we have discussed so far, if this sits on a special position, then it becomes if it sits on the symmetry element, it becomes a special position. So, in this particular case, the number of equivalent points generated will become only 1, because 0, 0, 0 will give rise to minus 0, minus 0, minus 0. So, it is half and half. So, that means the occupancy of this particular position when we are sitting at the center of symmetry becomes half. So, in this case the occupancy is full, this becomes half. So, there are 2 independent possible positions for this particular compound or the object, in this particular case molecule. One is related to the other by an inversion center. However, the number being 2 will reduce to 1 in case this sits on the inversion center, and that is how the possibility of having a centrosymmetric molecule occupy a molecule with an inversion center, how it can go and sit at the inversion center. So, the molecule now will be repeated onto itself, and therefore, we will get now only 1 equivalent point. Here there were 2 equivalent points, it becomes only 1 equivalent point, and the occupancy of that position now becomes half. So, that means only half the molecule, if there is a molecule of the type we discussed before, suppose this particular molecule is sitting at that 1 bar position, then this half of the molecule will be related to the other half. So, when you have to worry about is to determine only one half of the molecule. So, that way this is called the occupancy. So, the occupancy of that position becomes half. So, please note the whole idea of the first few classes which we have gone so far, as I mentioned also earlier, is to learn the grammar. We are actually learning the grammar. Once we have identified the alphabets, the so called point groups and all that will form the alphabetical notation in crystallographic language. And what we are trying to do is to develop the grammar, the various ways in which we can have an adverb, the way in which we can have an adjective in a language. So, the crystallographic language therefore has several new words introduced. Today, for example, we introduce equivalent points, we introduce the various symmetry elements called the inversion center, we set special positions, we set the occupancy. All these are individual grammatical terms which are necessary to develop a crystallographic knowledge. At this stage, we will stop today and then we will go forward in the coming classes. Thank you.